Hello all, today we are going to start Unit 5 Image Restoration. First, what is meant by image restoration? Image restoration is the process of recovering an image from a degraded version, usually a blurred and noisy image. Image restoration is a fundamental problem in image processing and it provides a test bed for more general inverse problem. Some image restoration techniques are best for modulated in the spatial domain, while others are better suited for the frequency domain. For example, spatial processing is applicable when the only degradation is additive noise. On the other hand, degradations such as image blur are difficult to approach in a spatial domain using a small filter mask. In this case, the frequency domain filter based on various criteria of optimality are the approaches of choice. These filters are also take into account the presence of noise. What is image restoration? Image restoration is to restore a degraded image back to the original image. Image enhancement is to manipulate the image so that it is suitable for the specific application. The figure shows how we can image restore. This figure represents the model of image degradation or restoration. The degradation process is modeled in this chapter as a degradation function that together with an additive noise term operate on an input image, that is f of xy, to produce a degraded image g of x, y. Given g of x, y, some knowledge about the degradation function h and some knowledge about additive noise term eta xy, and the objective of restoration is to obtain an estimate f cap x, y of the original image. We want to estimate to be as close as possible to the original input image, and in general the more we know about h and eta, the closer f cap xy will be to f of xy. The restoration approach used throughout this chapter is based on the various type of image restoration filter. If h is a linear position invariant process, then degraded image is given in the spatial domain by g of x, y is equal to f of x, y into h of x, y plus eta x, y, where h of x, y is the spatial representation of degradation function and the symbol star indicate convolution. We know from the discussion that convolution in the spatial domain is analogous to multiplication in frequency domain. So we write the above equation in an equivalent frequency domain representation is g of u, v is equal to f of u, v into h of u, v plus n of u, v, where f of x, y is input image, f cap x, y is estimated original image, g of x, y is degraded image, h of x, y is degradation function, and eta x, y is additive noise term. Then next topic is noise model. The principal sources of noise in a digital image is arise during the image acquisition and or transmission. The performance of imaging sensor is affected by a variety of factors such as environmental condition during image acquisition and by the quality of the sensing element themselves. For instance, in acquiring images with a CCD camera, light level and the sensor temperature are the major factors affecting the amount of noise in the resulting image. Images are corrupted during the transmission principally due to interference in the channel used for transmission. For example, an image is transmitted using a wireless network might be corrupted as a result of lightning or the other atmospheric disturbance. The sources of noise is image acquisition, or for a digitization is imaging sensor can be affected by ambient condition, and for the image transmission interference can be added to an image during transmission. Then what are the spatial properties of noise? Noise is in statistical behavior of the gray level value of the pixel and noise parameter correlation with the image. And the frequency properties of noise are Fourier spectrum, An example, white noise or a constant Fourier spectrum. This is all about the noise model. The spatial properties of a noise is whether the noise is correlated with the image, and frequency properties refer to the frequency content of a noise in the Fourier sense. For example, when the Fourier spectrum of noise is constant, the noise is called white noise. The terminology is a carryover from the physical property of white light, which contain nearly all the frequency in the visible spectrum in equal proportion. Then let us discuss about some important noise probability density function. Based on the assumptions, the spatial noise descriptor with which we shall be concerned in the statistical behavior of the intensity values in the noise component of the model. This may be considered random variable characterized by probability density function, that is PDF. First, we are discussed about Gaussian noise. Because of its mathematically tractability in both the spatial and frequency domain, Gaussian, it also called as a normal noise model, are used frequently in practice. In fact, this tractability is so convenient that it often results in Gaussian models being used in situations in which they are marginally applicable at best. The PDF means probability density function of a Gaussian random variable z is given by p of z is equal to 1 upon under root 2 pi sigma e raised to minus z bar square upon 2 sigma square, where z represents the intensity and z bar is the mean, means average value of z, and sigma is the standard deviation. The standard deviation square, sigma square, is called as a variance of z. A plot of this function is as shown in figure is approximately 70% of its value will be range from minus z bar minus sigma on minus z bar plus sigma, and about 95% will be range from z bar minus 2 sigma and z bar plus 2 sigma, or it is also denoted by mu. Then next type is Rayleigh noise. The PDF of Rayleigh noise is given by P of z is equal to 2 upon b minus z minus a e raised to minus z minus a square upon b for z is greater than or equal to a, and for 0 for z is less than a. The mean and the variance of this density are given by z bar is equal to a plus under root pi b by 4, and sigma square is equal to b 4 minus pi upon 4. The plot of Rayleigh density is as shown in figure. The displacement from the origin and the fact that the basic shape of this intensity is skewed to the right. The Rayleigh density can be quite useful for approximating skew histogram. Then next type is Airline, means gamma noise. The PDF of Airline gamma noise is given by P of z is equal to a raised to b z raised to b minus 1 upon b minus 1 factorial e raised to minus az for z is greater than or equal to 0, and p of z is 0 for z is less than 0, where the parameters are such that a is greater than 0 and b is a positive integer and factorized in is a factorial. The mean and the variance of this density are given by z bar is equal to b upon a and sigma square is equal to b upon a square. The plot of this density is as shown in figure. It also called as a gamma density. When the denominator is as shown, the density is more approximately called the Airline density. Then next type is exponential noise. The PDF of exponential noise is given by the formula P of z is equal to a e raised to minus az for z is greater than or equal to 0, and P of z is equal to 0 for z is less than 0, where a is greater than 0. The mean and the variance of these density functions are z bar is equal to 1 upon a and sigma square is equal to 1 upon a square. Note that this PDF is a special case of Airline PDF with b is equal to 1. The plot of this density function is as shown in figure. Then next is uniform noise. The PDF of uniform noise is given by the formula P of z is equal to 1 upon b minus a if z is sliced from a to b and P of z is 0 for otherwise. The mean of this density function is given by the formula z bar is equal to a plus b by 2, and the variance is given by the formula sigma square is equal to b minus a bracket square upon 12, and the plot for this uniform noise density is as shown in figure. Next type is impulse salt and pepper noise. The PDF of or the bipolar impulse noise is given by the formula P of z is equal to P of a for z is equal to a, P of z is equal to Pb for z is equal to b, and P of z is equal to 0 for otherwise. If b is greater than a, intensity b will appear as a light dot in the image. Conversely, level A will appear like a dot. If either PA or PB is 0, the impulse noise is called unipolar. If neither probability is 0, and especially if they are approximately equal, impulse noise values will resemble salt and pepper granules randomly distributed over the image. For this reason, bipolar impulse noise also is called salt and pepper noise. Data dropout and spike noise are also terms used to refer for this type of noise. This figure shows the plot of impulse or salt and pepper noise. Noise impulse can be negative or positive. Scaling usually is a part of image digitizing process because impulse corruption usually is a large compared with the strength of the image signal. Impulse noise generally is digitized as extreme, pure black or white values in an image. Thus, the assumption usually is that A and B are saturated value in the sense that they are equal to the minimum and the maximum allowed values in the digitized image. As a result, negative impulse appears at a dark paper point in an image. For the same reason, positive impulses appear as a white means salt noise. For an 8-bit image, this means typically that A is equal to 0 means black and B is equal to 255 white. The figure represents the PDF of impulse noise. The original figure represents the test pattern well suited for illustrating the noise model. This is suitable pattern to use because it is composed of simple constant area then span and grayscale from the black to near white in only 3 increments. This facilitates visual analysis of the characteristics of the various noise components added to the image. And the figure shows the test pattern, their addition of the 6 types of noise discussed shown below. Each image is the histogram computed directly from that image. The parameters of the noise were chosen in each case so that the histogram corresponding to the 3 intensity level in the test pattern would start to merge. This made the noise quite visible without obscuring the basic structure of underlying image. The histogram for the salt and pepper example has an extra peak at the white end of the intensity scale because noise component were pure black and white and the lighter component of the test pattern is light gray. With the exception of slightly different overall intensity, it is difficult to differentiate visually between first 5 images even though their histogram are significantly different. The salt and the pepper appearance of the image is corrupted by impulse noise is the only one that is visually indicative of the type of noise causing the degradation. This is all about the noise probability density function. Thank you guys.